Well, hi, this is Bob, and we're getting ready to take a look at Chapter 6, and I'm going to start discussing Section 6.1, which I think is one of the most interesting chapters that we'll run into in our class this semester. If you notice over on the top of page 312, this shouldn't come as too much of a surprise because I've been saying this for since pretty much the beginning of the class, but you may recall that we started off just drawing some bar graphs. We called them histograms. And if you notice on page, at the top of 312, they have like four different graphs, A, B, C, and D. And in particular, if you look at the C graph there, it looks, and remember where we're going with this is the bell curve, which I can't seem to write now, this pen, but I'd like you to notice that letter C on the top of page 12, it looks like it's composed of lots and lots and lots, it's not the best mathematical term, bars there. And the idea is the bars, there are infinitely number of bars. In other words, the sample size gets bigger. And of course, the greater the sample size, then the smaller the widths of our individual classes, if you like. So I'm just going to go ahead. And again, we've got a little bit of theory here, but most of this section is really practical introduction and application of the standard normal distribution tables. But I need to get just a little bit of theory out there so we can have a good idea of where these graphs came from. I will, as always, leave it to you to do a close read of the material, but I'm going to try to hit the high points here. But as our sample size increases, we see that the class widths get smaller. That's basically chapter 1, 2, and 3 stuff. And then finally, and I think the example they used here was if we took I think it was 100 adult women and measured their heights. By the way, I need to mention one other thing here, very important. We had two types of variables, discrete and continuous. And the standard normal distribution, which is where we're going, is based on continuous random variables. That's why you will see in letter D, which unfortunately I can't draw that well, but I'll approximate it. In letter D, on the top of page 312, this is our bell curve or our standard normal distribution. And if you notice, and what I'm trying to approximate here is all the area under that curve is shaded. Now, the previous one I did, they say, well, what if you took 100, and remember we're dealing with continuous variables, continuous random variables, and we know those are ones that represent things that are normally measured like height or temperature or weight, etc. And if graph C represented 100 women that we took the heights of and then plotted, then graph D, that normal distribution for the population, they say that represents all the women, the whole population of women. And let's see if I can find that there again real quick. If the heights of all adult females in the United States and plotted them, the histogram would approach what's called a normal distribution curve. And again, remember, we're not dealing with discrete variables, we're dealing with continuous variables, and we would end up with a theoretical curve That looks something like the graph D on the top of page 312. And this is called the normal distribution, and as I said, where we're going is the standard normal distribution. And they tell us that no variable fits a normal distribution perfectly. This is sort of a theoretical distribution. However, when we do our measurements, or when we're gathering data and then using that information and finding things like mean, median, mode, standard deviation, etc., those things can play, especially the mean and standard deviation and the population size. Those things can come into play when we're using the standard normal distribution, and we can use that to make probability or even make educated guesses, as we'll see in later chapters. But we first of all have to understand how this curve works. And normally we just call it the bell curve, but it's important that our book calls it the normal distribution. And just briefly what they mean on that is that half of the distribution, first of all, it's an idealized curve where the mean, median, and mode are at the center, and then 50% of the distribution is to the right of the mean, median, mode, and the other 50% is to the left. In other words, we would have a mean height if we were able to measure all the ladies in the United States, and 50% of, using this idealized curve as an example with the question there, we would certainly have a lot of ladies that were taller than the mean height and a lot of ladies that are less than the mean height. Okay, and so that's just some things to start talking about. The next thing I wanted to mention is over on page 315. We're not really interested in the mathematical equations because we're not going to use those when we're dealing with the curve. We have charts in the back of our book and possibly on the cover of your book that relate z-tables to the areas under that curve there. And that's how we're going to make our predictions and find probabilities later, and also do some decision making when we get into chapter 7 and chapter 8. Anyway, so I'd like you to read over the pages, all the pages in this chapter, but again, we're not really that interested in using the mathematical derivation of the curve. We only need how to use the curve in terms of application. Well, at the bottom of page 313, they show us that we can have a curve that has the same standard deviation, but different means, or we can have the same means but different standard deviations, but that's still a normal curve, and it would still have all these assumptions that we're going to talk about on the top of page 314. And a lot of these will come back and should make sense in terms of what we've seen before, and I've tried to make mention of some of the main ideas ahead of time in earlier chapters. Here's just a really informal summary of some things about that curve on page 314. The first thing that they tell us is this curve is bell-shaped. Okay, and then they tell us that the mean, median, and mode bisect the curve about right there. Remember, this is a theoretical distribution. Okay, and then they tell us that it's unimodal, which makes sense. In fact, in this idealized distribution, mean, median, and mode are all at the same location, and they cut the graph in half with 50% of the area to the right of the mean, median, and mode, and the other 50% to the left. So that's what they're coming with number 4. They say the curve is symmetrical about the mean, which is equivalent to saying that it is the same on both sides. and the vertical line passes through the center. If we were to fold each of these sides, they would fit perfectly on each other if this was our axes of folding, which might be another way to think about it here. Okay, then they tell us that the curve is continuous, that there are no gaps or holes, and for each x value, we'll talk about that shortly, there is a corresponding value of y. Although, as we'll see shortly, we don't normally we have the x-axis, but we're not really interested in heights or the y values here. We're interested in that area under the curve, and that pretty much sums it up. Curve is continuous, no gaps, but for each critical value of x, or each value of x, there is a corresponding value of y. Okay, then they tell us that the curve never touches the x-axis. You may remember from Algebra 105 that we have something called asymptotes, and they get closer and closer and closer. The curve gets closer and closer to the x-axis, but it never really reaches the x-axis or touches, and that's called an asymptote. And this is really important. The total area under the curve is 1, or 1.00. And notice that the 50% of the curve on the left and the 50% of the curve on the right can be expressed as decimals, which add up to 1. And by the way, we need some calculus in order to prove that the area goes to 1. And they would use something called a limit to do that. But again, we're accepting all this as they tell us, and we have no need to use any higher math than what we've already had. All we're doing is learning the features and how to use the curve. Okay, then the last thing you probably already, well, you should recall from Chapter 3. You may recall we had Chebyshev's distribution, and then shortly after we said, you know, the normal distribution or the empirical rule is what we use. And just it's at the bottom of page 314, but you may recall that if this is our mean, then within one standard deviation of the mean, 68% of our values fall in. 0.34 on one side and 0.34 on the other side. Technically it's 0.3413, but that's fine. I want you to look at the bottom of page 314 and see that graph, and that relates standard deviations and the mean. So standard deviation, or the mean plus one standard deviation, 0.3413 of the area of the graph falls to the right of the mean, and the mean minus one standard deviation. This area in here is 0.3413 also. So we know that the bell curve, this normal distribution, is symmetric, and we know that it has an overall area of 1. And by the way, it doesn't matter whether it's shaped like this or our distribution, oops, I didn't mean to have our pen slip there. You know, they show it like this, but we could, our distribution that we went out and did some samples for might look more bunched up. In other words, the standard deviations might be different. Okay, but again, the area for both of these curves would be considered to be equal to 1. And we can go and use the tables that relate the areas to probabilities, and that's coming in just a few minutes here. Okay, well, there's some other things. So I'll just tell you right now that for the problems that we're going to be working throughout pretty much all of the class that's left, they're going to tell us whenever we go to solve a problem that we can consider or assume that there is normal distribution. And I'll talk a little bit more about that in a second. But when we use the standard or the normal distribution, we normally would have to take a look at our data and make sure that it's not skewed, or basically it's good data. And normally if you have over 30, if you've done your sampling correctly and you have a n greater than or equal to 30, you will get a normal distribution. But the other thing that's going on here is that the book tells us that we can, when they give us a particular problem with some information like the mean and a individual random value of x and a standard deviation, no matter whether they give it to us the population or a sample, normally we'll be dealing with an established mean, and we're going to have a sample mean or a sample. But the point again is that we can assume normal distribution. And the book will tell us that. But they make it a point over on the top of page 315. First of all, they show us the distribution that we're going to be using. That's A. And they show us where the mean and the median and the mode are smack in the middle. In other words, it bisects the curve. Well, then they show us on B a negatively skewed, pushed to one side, and it tells us when we're talking about negative skewed that majority of data values fall to the right of the mean, and the distribution is said to be negative or left skewed. Okay? And then they tell us when the majority of the data values fall to the left of the mean, the distribution is said to be positive or right skewed distribution. Okay, well you can look at those, and again, we're interested in situations for our class where the book will have already gone out and got the results that we need for us to start using the normal distribution. But in case you're curious, there was something that we've seen on this before, and it was on page 147. I won't be having any questions on this, but I think it's important that we're aware of it. And this talks about the Pearson coefficient, and it's basically a formula. And the formula says you take 3 times the sample mean. In parentheses, we have the sample mean minus the median, and then that gets divided by the sample standard deviation. Now, this is a check for skewedness. And the values run from -3 to 3. Okay, now if you get an answer around 0, that means that the data values that you have, for which you figured out the sample mean and the median and the sample standard deviation, if you get a value around 0, that means that the data that you have collected is approximately symmetric. If you get a value that is negative, then that means that it's negatively skewed. And if you get a value that's positive, like maybe 2.5 or even 3 or 1, that means that the data is positively skewed. So there is a way for us ahead of time, not necessarily in our class, but in a real-world situation, if you wanted to check the data, you could use this particular equation. And it was actually on number 48 on page 147. Anyway, we're finally going to get to it here on the questions. We've got one more little rule to see here, and this is on about halfway down on page 315, the standard normal distribution. And they tell us that it has a mean of 0 and a standard deviation of 1. Okay, now what we're going to do is we're going to be switching things into z-values. And we access the curve using z-values. In other words, the z-value of 0 is the symmetry point or line on the curve. And the z-values basically go from like 0 to 3.49 positive on the right side of the curve, and in the left direction to 0 to minus 0.349. And these are referenced in our tables. Some of you may have got a plasticized pullout with your text. And in our old book, the tables were on the front cover, with the inside cover and first page of the book. Now the tables, at least in my book, are back on page 788 and 789. Okay, and what we've got is, we'll really go into detail on this, but on one set of the tables we have the positive z-values, and then on the other side we have the negative z-values. And you may recall that in order for us to find a z-value, we've done this before, you did it a couple of times on the first test and lots of homework problems. We take our value, subtract the mean, and we divide by the standard deviation. Or in symbols, our z-value equals x, our value, oops, getting ahead of myself here, let me get a fresh page. Our z-value equals x minus the mean divided by the standard deviation. Okay, here's the other thing I mentioned, but I'll mention it one more time. The z-value, or let me go a little bit ahead of myself here. Well, I think this was it. The z-value or z-score is actually the number of standard deviations that a particular value is away from the mean. Okay, so when we look up, when we have a z-value of 0, if you put the mean in, and if our x is the mean, and we subtract the mean from the mean and divide by standard deviation, we get 0 on top, and so 0 is the equals a z-value of basically what we're saying here is 0. And then we have standard deviation 1, 2, 3 standard deviations above the mean, and then minus 1, minus 2, and minus 3 standard deviations below the mean. But a z-value of 0 is the symmetry line for our graph. Somewhere there was something else I wanted to mention, but I can't seem to find it now, so I will come back to it. But what you should be doing right now, because I'm going to do every one of these examples and some homework questions, is there are several different situations, and this is critical to move on in the class. There are several different situations that we need to be able to find values on the graph. And those are shown on the bottom of page 316 and the top of page 317. And you need to know how to use the tables for each of those situations. Now, the first thing, and I'm assuming that you have your tables out, we'll do just one for positive. here is our z-value, and they run down this way. And then on the right, in other words, this would be our column, and then stretched out in our row here is we have different z-value numbers. And if we wanted to start off where they start off, we would have like a z-value of 0.00, and then they start going up. And on page 317, that first example shows us where we have a z-value of 1.3. That's basically a z-value. Here's 0. Here's 1.3. And we want to know the area associated with that. And as I'll explain in great detail, the way our graph works, or our charts work, is the area to the left of that 1.3 is what's represented in the table. Okay, so when they say a z-value of 1.3, they want the area, or our table provides us with the, it's understood to give us the area to the left of 1.3. Actually, this is, recall that that's 50% already. And we run down the table there to where we found out, I'm sorry, it was 1.39. And then we find out the 1.3 in the vertical column, and we find the 0.09 in the row, and then we come down and find out where they meet at 0.9177. In other words, I'll show exactly what this means. If somebody asked us to find the area associated with a z-value of 1.39, and if they phrased the question thusly, what's the area to the left of where z equals 1.39, then this is what they're talking about. And that area there, as we've just found, would be 0.9177, or as a percent, 91.77%. And that we're going to see very shortly that the area under our normal distribution also represents probability. Okay, well, I'm going to very carefully work through each of the examples and explain what we're looking for in terms of using this curve here. And the first thing, and if there's one thing I can stress in this class, it's always sketch the curve. For example, the first question asked finds the area under the standard normal distribution to the left of z equals 2.09. Here's what they're asking for. Doesn't have to be a good sketch, by the way, but 2.09 on my graph, I'll say, is right there. I clearly know now what they're looking for because there are many different tables. There are condensed tables, and we're fortunate that we have both the positive and negative z-values on two separate tables, but they still take some finessing and getting to understand. In an earlier edition of this text, we only had one table, and so we had to learn a particular way to handle that table. But if you identify what you're looking for, then it's just a matter of going to the table. And what you would be doing on this one is you would look for a z-value of 2.0 here, and then you would go find the 0.9 in the as far right corner as you can, which is hard for me to, but I'll say the 0.09 is right here. By the way, if you take 2.0 and 0.09, it's kind of like our stem and leaf that we saw earlier. Of course, you get 2.09. and the value associated with 2.09 is 0.9817. Okay, so this is the type of homework you'll be doing, and it's going to be very hard to move on to the class because we're going to need to know how to look up values from our table. Okay, well, let's take a look at 6.2 and see what's different there. Okay, this time we want the area to the right. So here's our standard curve again. We want the area to the right of minus 1.14. Okay, well, there's more than one way to do this, but there's only one recommended way with our tables here. So what we're going to do, and by the way, keep in mind, just to give you some kind of an idea for an answer, you better get an answer that's above 0.50 because this area right here is 0.50 already. Okay, so what we're looking for here, for when we get an answer, it has to be bigger than 0.50. Okay, so in this case it tells us, and again this is 6.2 on page 318. Well, the way they approach it is we keep in mind that everything under this curve adds up to 1. When you use the negative z-tables, they give you the area to the left of the z-value. In other words, you can read directly what this area right here is. It's like our complement. So here's what we're going to do. We know this area is bigger than 50%, but what we're going to do is we can read the area to the left of minus 1.14, and when I get that, I'm going to subtract it from 1, and that will give me all the area to the right, which is what we're looking for. So you would go to the tables, and you would find minus 1.1. Here's your z-value. Here's 1.1, and then you would want like 0.04 on the other part of it there. I'm just going to kind of dummy it in there for our sake. And when you find that, it turns out to be, I'm looking at my table, but it's in the book also. It tells us it's 0.1271. This area right here is 0.1271. But that's not the area we're looking for, that's the complement. So what I'm going to do is I'm going to go 1 minus 0.1271. And that is equal to, according to the book, 0.8729. And that's the area that we were looking for. Okay, well once, there's only like 4 or 5 different situations, and once we understand each situation by drawing a picture, then it's pretty tough to go wrong. If you try to just kind of guess your way through this, it's so easy to make a mistake and end up with a complement instead of the answer that you were looking for all along. Okay, well here's another possibility. This is example 6.3. This time we want the area under the standard normal distribution between z equals 1.62 and z equals minus 1.35. Okay, there's where z equals 0, bisects the graph, and then we've got just a sketch, 1.62, and minus 1.35. It doesn't have to be a good drawing, it just has to depict what I'm looking for here. Now, the best way to do this, would be to use the complement again, and I'll just try to explain what's happening here and the way I would approach this problem, okay, because there are a couple of different ways that can be done, but we'll stay with the book. We can find all the area between 1.62 and all the way to the end of the curve, okay? Then we can also find the area to the left of z equals 1.35. We can find this area. Okay, if we find the area to the left of 1.62, and we subtract the area to the left of minus 1.35, that will give us our answer. So, and keep in mind that you can never get a negative area, okay? So the way we're going to do this is we're going to find all the area to the left of 1.62, and then we're going, that's too much though, because that counts this area here. Then we're going to subtract out the area that's associated with minus 1.35. Okay, and the book tells us that the area to the left of 1.62 is 0.9474. And they tell us the area to the left of minus 1.35 is 0.0885. And when we subtract the smaller number from the larger number there, we end up with 0.8589. Or 85.89% of area of the graph. Okay. Well, now that we've learned how to find areas, well, then they tell us on the reading at the bottom of 318 and 319 that the areas are associated with probabilities. We're talking about being able to use the area under the curve and relate those to the probability of different events happening, as we will be doing shortly. And we'll see some other situations here. Okay, so here's the first one we want to see. It's basically the same thing that we did, except now we're going to call the area probability. So what is the probability of the area which can be related? Find the probability for each. This is example 5.4. And we want the area, but we're going to call it probability of a z that's bigger than 0 and less than 2.53. Okay, let's draw a picture of that. Always draw a picture. Okay, well, right away we know that we're not going to get an answer that's bigger than 0.50 here, okay? But so the first thing I would point out, and I'm sure that you've picked up on this area to the left of the curve is not shaded, okay? So there's no way that we can count that. In order for us to use the table, we can go right to the table and find out the z value associated with 2.53, but that's going to give us all the area to the left of 2.53. But once we get that area, to the left of z.253, we'll just simply subtract 50% or 0.50 from it. Okay, but remember 2.53 is a z value, and we're going to take the area associated with that z value and subtract 0.50. We don't mix those two up. Okay, well, so back to our situation. Here's 2.53. Here's the 0.50 we're going to subtract out. when we go in our book, they tell us that the area to the left of 2.53 is 0.9943. Here's what we're looking for. But when we look up the area for z equals 2.53, it gives us everything, which is 0.9943. Okay, well, what we have to do is subtract out this 50% that we weren't interested in. And of course, we get 49.43%. As a decimal or as a percent. So if we're talking about a probability here, and remember that the topic we're working on now, they tell us that the normal distribution curve has a probability distribution curve. So the area can be turned into probability. So if we wanted to relate that area to a situation in terms of a probability, we could say that the probability is equal to the area, or 49.43%. Okay, let's look at this second one there, and this one we can read directly. Here's the second situation. This is a probability of z less than 1.73. Okay, well, from drawing the picture, here's z equals 0. Here's 1.73. We know from our table, well, first of all, we know that this is what they're interested in. All this here. Okay, and we can read that directly because that's the way the table works. And by the way, make sure that you look at the very bottom of the negative and positive z tables. Notice what they do. I'm going to show you the bottom now of the table. They show a 0 and a z, and then they show everything to the left of it. And then they label this as area. That's the way the positive z tables work. And you can look and see how the negative z tables work also. All right, for this situation, we can look it up directly. And it turns out that the area is equal to, oh wait, did I miscopy that? No, that's fine. 1.73, and that is equal to 0.9582, or 95.82%. Okay. So it's the third one that's a little different, and this is the probability that z is greater than 1.98. Okay, we're in that right tail now. Let's say that 1.98, we're about 2 standard deviations above the mean, and we're interested in this area right here. Well, let's see if this makes sense. Our tables will tell us what everything to the left of 1.98 is, and once we find that, we'll subtract it from 1, and what will be left will be basically this area here, which would be like its complement. So the area to the left of 1.98, they tell us, is 0.9761. Okay, that's all of this area here, 0.9761, and if we subtract, we know the whole area of the curve is 1.00, so if we take 1.00 or 1 and subtract 0.9761, which excuse me, leaves us with 0.0239, that is exactly the area that's in that right tail there, or as a probability of the 2.39%. Okay, well, we've got one more to do here. Then I'm going to go do some homework questions. Let's do the z-value under the standard normal distribution. We've done one. Oh, we're going backwards now. In the sense of what we've shown already. See what's different about this situation. This time, we want the z-value. That's associated with an area, in fact, it's this area, 0.2123. Okay, so what z-value is associated with that area? Now remember, we're only interested in this area to the right of 0, but the z-value that would be related to it would be the same if we're doing this properly. And you may recall that in other words, what we're going to do this time is we're going to go into the actual tables and find the value that associates itself with 0.2123. However, our tables don't work that way, but we can recall that 50% of the graph is to the left there, and that we can find a z-value that's represented by 0.50 or 00 if you like, and 0.2123 or 0.7123. Okay, so what we're going, and that z-value is our answer. So we will go in our table. They show this at the very bottom of page 320. What they're doing in this case is they've got a z-value, and then they show a 0.06, and we had and a 0.5. I'll get down to that in a second here. Okay, so what they've done is, and you should verify this in your positive z-tables, if you go look at the areas there, this time they have found an area, and remember where we got that area, we added the 0.2123 and the 0.50 and got 0.7123. Now we go into the actual values in the table, and we find that 0.7123, and we go up and over, or left and top, or left and up. Anyway, we get, in the z column, we get 0.5, and to that we're going to add 0.06, going this direction, or 0.56. So a z-value of 0.56 is the value that would be related to an area of 0.2. In other words, I'll just draw the picture of what we're talking about here. Here's our area of 0.2123, and this is our z-value that we found out of 0.56. And that z equals 0.56 is associated with an area of 0.2123, or that much area to the right of where z equals 0. Okay, well, you will be doing lots of these types of questions. The only way to really get comfortable and good using the tables is to do some homework questions. But I thought I would close off by looking at question 49, which you can follow along with, and we will be using these particular numbers a lot. It says we want to find two z-values, one positive and one negative, that are equidistant from the mean so that the areas in the two tails add to the following values. That's really wordy, but by the time you get over to this number 49, it will make more sense. We've already worked every possible situation. We want there to be in the two tails, as we'll see in chapter 8, that's where things start to happen. We want to divide up 5% of the area in each of those two tails. And so what we would do is we would turn 5% into a decimal and divide by 2. And it turns out when you divide 0.05 by 2, we get 0.025. So 0.025 of the area will be in the right tail. Let's put z equals 0 there. And we'll put 0.025 in the left tail. Now, fortunately, since there's symmetry, all we have to do is find one of the z-values. We'll find the positive one, and then we'll take its opposite for the negative one. Now, the next thing we need to do, and this is where I think you'll see the problem isn't quite so bad, is remember in the table that the table will give us, in other words, if all this area in the table is 1.00, if we subtract 0.025 from 1, it leaves us 0.9750. Okay, so that means that if this is 0.025 of the area in that right tail, that the rest of the area is 0.9750. So here's what we can do. We can go into our tables and find the z-value that associates with 0.9750. And that will that z-value then will represent the area of 0.025, and then, as I said, we'll take its opposite and for the left tail. So when we go look for 0.9750 in the positive z-tables, we end up with 1.96. Okay. Now, again, the area to the left of 1.96 is 0.9750, so 1 minus 0.9750 equals 0.025. So if our positive z-value is 1.96, then our negative z-value will be its opposite, or minus 1.96. So those are our two answers. Now, I chose to work this odd one because it'll be worked out for you in your solution key. Let's do one more of these before we'll stop. We will do 10%. Same problem, just a different percent. These are going to come back in chapter 8, and you'll be using them all the time. So what we want to do is take 10% or 0.10, and we want to cut it into the right and left tail. Always draw a picture. So since we got two tails, we got to divide by 2, and that turns out to be 0.05. So there will be 0.05 area in the right tail, and there will be 0.05 area in the left tail. Now, what we're looking for is this z-value, and the way that we would phrase the question is, what's the z-value that has 5% of the graph to the right of it, or in that right tail? So remember again from our tables, if we subtract 0.05 from 1.00, we get 0.9500. So what we're basically saying here is that there will be 0.95 00 of the area to the left of this 0.05 here. Doesn't matter whether we count the other 05 again, it's already there, okay? So what I'm going to do now is I'm going to go into my tables and look at the values, and I'm going to find the value of 0.9500, or the closest value to it. And when I do that, I'm halfway between like 1.6, the value for 1.64 is 0.9495, and the value for 1.65 is 0.9505. Well, they're both equidistant. I'm going to use the larger one, which is so we're going to go with 1.65. So the z-value that represents 5% of the area, that has 5% of the area to the right of it, even though my graph may not look that good, is 1.65. And remember, we wanted to have 5% of the graph in each tail, or 10% overall. So if our positive z-value was 1.65, then our negative z-value would be minus 1.65. Okay, I'll leave it for you to do the last one there, 0.005, or to divide 1% and split it into the tails, and use my example here and your solution key for some help. Again, I can't stress how important it is to be able to use our tables to find these different values in the different situations. So please be sure to reference my eLive here and your solution key, and let me know of any questions, and I'll help the best I can. But I can't stress it enough. We need to know how to use those z-tables to continue on in the class for Chapter 7 and Chapter 8. I'll be back shortly with 6.2. Thank you.